Okay, so this is the Centripetal Force lab, and what I have here is what we like to call the cage, and it's a solid cylinder connected to a spring, and as this rotates, the mass wants to go straight, but the spring will keep the mass going in a circle. The spring will be providing the centripetal force. So one of the first things we're going to do, we're going to have to measure that spring force. Okay, so when you hang the mass on here, you're going to extend the spring, and maybe you can see the little pointer. The pointer will go up and down, and you want it at the point where it's just pointing right at that little button. Now, the mass of the cylinder is something that you'll need to know, and I'll send that to you in your data set. It's around 150 grams. So over here, I've got one that I've set up, and if Dr. Variano can zoom in on the little pointer, I've got the masses hanging here, and that pointer should be pointing pretty close to the little button. One of the things that you would measure in the lab also is the distance from the axis of rotation to the center of the mass. And we use a set of calipers and measure from, about right here, this is a little bit tricky, to the center of mass of the solid cylinder. So that's about 57 millimeters, something like that, which we'll need to put in meters. Okay, so once we measure the spring force, and I'll show you in the calculation segment how we're going to calculate that and how we're going to manipulate the spring force, we'll compare that spring force to the centripetal force once we have it in the rotator. Okay, so now I've placed the mass spring assembly in the rotator, and what we're going to do is rotate this thing up. And what happens with Newton's first law? It wants to go straight, but the spring is keeping it from going straight, so the spring is going to provide that centripetal force for the mass. So as this thing spins faster and faster and faster, it's going to need more and more centripetal force to keep it moving in a circle, and that mass will move out, and we want it to move out until the pointer, that's, maybe you can see it right down there, points right at what I call the little button. So once that pointer points at the little button, that's the same situation we had where the mass was hanging and we had the extra masses or the masses on, hanging masses on it to make that little pointer point at the button. So here we go. Let me see if I can show you this. So watch the little pointer. Right, so the pointer's still below the little button. I'm speeding it up, I'm speeding it up. This is tricky. Very sensitive. I see it trying to come up just a little bit, I think. Okay. Come on. Come on. All right, it's pretty close. It's a little high. Let me see if I can get it lower. Oop, too low. Very sensitive. Too high. That's pretty good right there. Okay? So that's what we're looking for. And then once we have that value, we'll read the RPMs off of the rotator, and then you'll be able to do the calculation. Okay, so once we've done what we just did with the pointer and making, getting the RPMs up enough where that pointer points right at the little button, then you want to read that frequency off of the rotator, and this is in revolutions per minute. So that's 510 revolutions per minute. And when we actually do the calculations, you'll need to put that in revs per second. Okay, so now we'll talk about the calculations that we'll have to do for the centripetal force procedure. Here's a little drawing of the setup that we had. Here's the spring, the little cylindrical mass, which I'll call little m, and then the hanging mass, just lump it all into big M. All right, so the spring force that's being exerted on the little mass, if we just look at the free body diagram of that, that's little mg plus the force that's being exerted from the hanging mass, which is big mg. So the spring force is little m plus big mg. Okay? I'm going to send you values for big M, little m, r that we measured. That was that radius, what I'll call the radius of the circle that it goes around in. Delta M will be the uncertainty in the hanging mass, and delta little r will be the uncertainty in that radius that I measured when I had it hanging. So delta Fs is equal to delta big M times g. So you'll get a value for the spring force plus or minus delta Fs, and that gives you a range for the spring force. Now, let's go to what I would call part two, where we put the cage in the rotator, started it rotating. We know from what we've done in class that when an object's in rotation, uniform circular motion, what keeps it going in a circle is this so-called centripetal force. So for an object that's rotating in a circle of radius r at a tangential velocity v and mass m, that centripetal force is equal to mv squared over r. That's the mass times the acceleration. I'm going to give you a value for the frequency and the uncertainty in the frequency. The tangential velocity is equal to 2 pi r, that's the distance around, multiplied by the frequency. That gives you the tangential velocity. So v squared works out to be 4 pi squared r squared f squared. Then we divide that by r, and you get for the centripetal force little m times 4 pi squared r, because the cancellation of the r, times f squared. And you need to make sure that that's in kilogram meters per second squared. So you'll have to convert the grams for little m to kilograms. You'll also have to convert the RPMs for f to revolutions per second. Okay, then to calculate delta FC, that's the uncertainty in the centripetal force. That is the centripetal force that you just calculated here, multiplied by delta R over R, plus 2 delta F divided by F. So just like we had over here with the spring force, the centripetal force plus or minus delta FC, that gives you a range for the centripetal force. These two values should agree within the limits of uncertainty because the spring is providing the centripetal force to keep that mass moving in a circle.